So let's go ahead and start section 1.2. It's called Functions and Their Properties. There's some really important information in this section about domains of functions, and I know that that was kind of a struggle during the first week when we were doing the review. A lot of people are struggling with the idea of domain, so that will be introduced in this section and other things like that. Now, it is a lengthy section, and there's a lot of important information in it, but I don't think much of it is very difficult. There's just a lot of information. It's very lengthy. So let's just see how far we can get today. Since we're splitting it over 3 days, it's not even really a big deal how far I get. Cool? And then when you go to do the homework tonight, please do, just go as far into the homework as I went in the notes and then stop. And you'll be set. We begin by talking about, again, domain and range. So this is some really fancy stuff, and rather than read you the fancy stuff, I'll just tell you domain means the input values, usually x's. Range are the output values, usually y's. A function has exactly one y for every x. You say that again and a little bit different. For every x, there is exactly one y. Never two y's for a single x. Imagine if I told you x equals 3, and then I said y equals 1 and 5. Those would be 2 points that are vertical to one another, like this. And that would fail good old vertical line test. So in order to be a function, there can only be one y for every x. Now, it's okay for different x's to point to the same y's. You see, that's not a problem. Like right here, I have x3 and x4 both pointing at the same y value. That's not a big deal. I mean, think about a parabola. It points up or down on both sides of it, right? So for every parabola, there will be more than one x that hit the same y. That's what this is doing. So this is not a problem. This is still a function. This one right here, x1, is breaking the rules of a function, and that's why this set is not a function, because you have a single x pointing to 2 different y values. That's not allowed. That's what's causing the problem there. When you're looking at a graph itself, honestly, just the vertical line test. If a vertical line can hit your graph in 2 places anywhere, then it is not a function, because that's one x that has more than one y. But as long as every single vertical line you draw can only touch the graph once, you have a function. So we're looking at these 3. One of them is not a function. Which one would it be? C. Of course, because I could draw several vertical lines that hit that guy in more than one place. So clearly, it's C. This one fails the vertical line test. Very simple. Just by looking. All right. So, we're going to be focusing on functions for most of this year. So we might as well talk about how to find the domain of a function algebraically. Without graphing, we should be able to figure out what x's are allowed to exist for a function. We should be able to do that algebraically. And we had one like this in the review material talking about the domain of a square root function. And the way that I approached this when students asked me for help was I said, okay, well, let's talk about it. What kind of numbers are you not allowed to take a square root of in the real number system? And we would say, negatives. Yeah, Damien's right. Yeah, we can't take the square root of a negative number in the real number system. And since we will not be graphing in the complex number system this year, and yes, that's a possibility, but since we will not be doing it in this course, we're going to only be talking about things that can exist in the real number system. So if I cannot take the square root of negative numbers, I must be able to figure out then what is the smallest absolutely the smallest value. There we go. I don't want to say absolute value. Absolutely the smallest value that could be underneath a radical in the real number system. Well, specifically a square root. is 0. Yeah. So if you would like to know where this thing's domain begins, you just figure out what makes the inside equal 0. So since it is a square root function, specifically square root or fourth root or sixth root or eighth root, even roots, you cannot take the even root of a negative number in the real number system. What we do is we set the inside of our square root function to greater than or equal to 0, because it's okay if it's 0. It's just not allowed to be negative, so it must be greater than or equal to 0. And then you just subtract 3 from both sides, and this will tell you that your domain is x is greater than or equal to negative 3. Now, we don't like inequalities in this course. We're a little bit more intelligent than that now, so we're going to write this as an interval notation. This interval says all the numbers to the right of negative 3, but including negative 3 because of the equal to sign. So bracket negative 3, comma, positive infinity, parenthesis, never put a bracket on an infinity. There we go. No, I like question B. I like question B because, well, I'm a nerd, and there's more than one rule at play here. First, the overall structure of our function is it's a fraction. And there is one rule about fractions that you have to know. You can't divide by 0. That's the biggest, most important rule about fractions. You can't divide by 0. So first and foremost, you should be able to look right here and say, wow, if x was 5, the denominator would be 0. That's not allowed. So I already know that x cannot be the number 5. But you know what? That is not the whole story. The reason why? This one also has a square root bar in it somewhere. And just like we talked about in part A, the smallest thing that could be inside a square root bar is 0. So we go, all right, just like we did for part A, we're going to figure out what's underneath the square root bar. We're going to set it greater than or equal to 0. So we go, okay, oh, it's just x. Oh, okay, so x has to be greater than or equal to 0. So this says all numbers beginning at 0 and heading to the right. However, this says, but you can't use the number 5. So that means all numbers greater than or equal to 0 except 5 is our domain. How do we write that as an interval? Well, we begin at 0. So bracket because it's included. And we get all the way up to the number 5. But we can't include 5 because, well, it's a no-no on the bottom, right? So you use a parenthesis. Yes, Damien?
I don't understand, like, why can't you use 5?
Because if you've used 5, you'd have the square root of 5 divided by 0. And you can't divide by 0. So because it's a fraction, you just figure out what makes the bottom equal 0. That's not allowed to happen. But 6 works, right? 5.1 works, right? So really, the only number that's a problem is 5 after 0. So what you're going to do is you're going to string it together with a union symbol, and you will begin at 5 again, just don't include it, and then never stop. So that is how you say all real numbers greater than or equal to 0 except for the number 5. That's how that works. And C. What we have here is a of x, some weird fraction, root 3 over 4, x squared. That's a parabola, right? Normally, parabola's domain, all real numbers. You could square anything you want, can't you? So normally, it would be all real numbers. But we've got this little blurb afterwards that says, by the way, a of x represents the area of a triangle where the side length is x. So immediately, you cannot say all real numbers because all real numbers include negative numbers. You ever seen a triangle with a negative side length? That doesn't make any sense, does it? You ever seen a triangle with a side length of 0? No, that doesn't make any sense either. So even though it is a quadratic, its domain is not all real numbers. We're talking about something in the real world. So its domain begins at the smallest values that we can imagine for the length of a triangle. And basically that just means any number that's bigger than 0. And that's it. See, normally quadratics do have a domain of negative infinity to positive infinity, but since this one is the real deal, it's an actual triangle, we're going to say that its domain will begin at 0 but not include 0 because it's not a triangle if the side length is 0. But then afterwards, you know, it could be as big as it wants to be. And that's why that one begins at 0 but not including 0. A little bit tricky. Are we comfortable with being able to find domains of, well, at least these kinds of things? Okay. I will tell you that I will challenge you with finding domains of functions in the homework and on the assessments. It won't just be a simple radical. It won't just be a simple fraction. It'll be radicals in fractions on the top or on the bottom, or a fraction underneath a radical bar. And we're always trying to make sure that the inside of a radical is positive, and we're always trying to make sure that the bottom of a fraction is never 0. Those are the two big problems. And sometimes that will include using sine diagrams. Remember when I showed you the polynomial inequality? I could put a quadratic underneath a radical on the bottom of a fraction and then say, what's the domain of this function? And you go, okay, first and foremost, whatever's underneath the radical has to be a positive number. That would be a quadratic inequality. You'd have to set up the sine diagram and figure out where your quadratic is positive. And then you also have to make sure that it doesn't equal 0. So that it would be non-inclusive for the zeros of that quadratic. I mean, there's just a lot of neat stuff, and like I said, I will challenge you in the homework. Feel free to send me reminds, should you need to. Okay. How about range? Am I going to be expecting you to find the range of a function algebraically? No, I do not. What I do expect you to be able to do is look at a picture and tell me what the range is by looking at the picture. So this says use a graphing calculator to find the range. You don't have a graphing calculator? Then use Desmos. I'm not asking you to find range algebraically. It is a very difficult thing to do. I want you to be able to look at a picture of a function and tell me what you see its range is. So I will go ahead and pretend that we broke out our graphing calculator, and I will sketch the graph of 2 over x. Here's the graph of 2 over x. This is called a reciprocal function. You don't need to know that term yet. I'm just letting you know. The range is the y values that this graph covers up. The arrow implies that this thing goes on forever and will continue getting closer and closer and closer to the x-axis. It's just not going to touch it. And this arrow implies that it's going up forever, getting closer and closer and closer to the y-axis, just not going to touch it. So if you had to describe the y values that this graph is hitting, what could you say? Anybody think they have an idea for me? It's okay to be wrong, just thinking, what could you say? Yeah, that's feeling good. Timio says it's going to hit everything except for 0. 0. He's right. Its range is all real numbers except for 0. So how would we write that range as interval notation? That's the question. Well, it's like saying everything except for 5. Question for me?
No, I was just going to answer it.
Okay, so I will have you do that for me in just a second. What we're going to show is that the graph shows that y cannot be 0. So Colin, how would you write that as interval notation?
Well, first I would have a parentheses, and I'd have negative infinity, comma 0.
Good.
Then I'd have a union.
Yeah.
And then I'd have 0.
Mm-hmm.
Parentheses, positive infinity.
Perfect. That describes all of the numbers except for 0. There you go. That's exactly how you would do that. Ta-da! That's it. So yeah, if you don't have a graphing calculator, Desmos. Hopefully everybody's familiar with Desmos.com. It's an amazing graphing program. I love it. And it can do something that your calculator can't do. Desmos can graph non-functions. Desmos can graph vertical lines. Your calculator can't. Yes, sir. Absolutely.
Did something wrong.
Let's see.
The graph kind of looks like that.
Woo! Look at his Look at his calculator did. Holy smokes!
How do you even type that in?
Yeah, I just did like 2 divided by x.
Interesting. It says you have an inequality graphing app on. Inequality graphing app. So it's trying to shade. Let's see.
There's one on R6 on the flag. And they use the 9.
There you go.
Okay, thanks.
I just reset the RAM of the calculator because I don't know how you turned that app on.
Okay, thanks.
Yep. If I knew how to turn it off, I would have. So that just made it onto the video. Now all of YouTube will know how to reset the RAM of a calculator. Yep. Oh, I've seen it a million times. You would not have been expected to know that yet.
So it's like, so how would I like figure out that? Like I have to type it in the graph.
Oh yeah, you gotta graph it. Yep.
Okay.
So you actually ask a graphing calculator to graph it, or ask Desmos to graph it.
Alright.
Yeah,
So
I mean,
wouldn't like know that off the top of my head.
not yet.
Okay.
You will soon.
Okay.
Okay. Yep. One more question about a calculator.
Every time I try and do it, it does that.
Invalid dimension. Okay, so this is important, guys. If you ever see this message, invalid dimension, that usually means that your window is all kinds of borked. So I'm gonna go to window. Okay, first I'm gonna hit quit, and I'm gonna go to window. And let's see, -10 to +10, 1, -10 to +10, 1. That doesn't look like a problem. Let's go to y equals. You have stat plots turned on. So you guys see where plot 2 and plot 3 are blackened?
Yeah.
That means the calculator is trying to do scatter plot as well. So we need to shut the scatter plots off simply by highlighting and then press enter. There you go. These are really good. I'm glad you guys are bringing up these calculators because they're making it onto the YouTube video. Yes, ma'am? No, you cannot. But on the test, I would have given you a picture and just said, what's the range? And you just look at it and you click on it. Guys, hey, so clearing the RAM is actually in the memory. So it's going to be second and then mem. On the bottom right-hand side, one of your buttons, it says mem above it. And then you just go to reset all. Be careful, though, because if you have any programs on there that you love, it will erase them. Yeah. Like games, quadratic solvers, things like that. There can be. Well, ask him after you Google it. Hold on. We are now going to introduce a concept known as continuity. And I'm just going to go ahead and preface this with, I disagree with your authors on their definition of continuity. And I'm not the only one. Ms. Bluebaum, the AP Calculus teacher, does as well. And actually, I'll just go ahead and say it. The authors are wrong. Their definition of continuity is poor. It is not good. So then why is it here? Well, because in mathematics, sometimes, unfortunately, we have to teach you things that you don't understand yet. And we say, in the future, you will understand it better. And continuity is one of those things. Because I can't give you a good definition of continuity until I teach you some calculus. So for now, we will discuss what our authors call continuity. I'll tell you why I disagree with them. And then in quarter 4, when I get to introduce some AP Calculus material, I'll get to redefine continuity, and then it'll be correct. So let's just go with what the authors are saying for now. A graph is said to be continuous if it has no breaks in it. It needs to be smooth, uninterrupted curve. Okay. So formally, this means that for any value of a, any x value you wanted to plug in, the output of the function, meaning the y value, will be close to what you would have gotten if you had plugged in that number A. What a weird thing to say, right? For now, let's just go with smooth, uninterrupted, and no breaks. So this, what looks like fourth degree polynomial, quartic, it's continuous. Look how pretty it is. Smooth, uninterrupted, and no breaks. Whereas this one has what we call a jump discontinuity. And what we're doing right now is learning about the different types of discontinuities. And yes, on the test, there's questions that are like, what kind of discontinuity are you looking at? And you would just choose, like, jump. Okay? So what does it mean to be a jump discontinuity? It means that at a certain point, any x we wanted, it didn't have to be on the x-axis. The entire graph picks up and goes somewhere else, vertically or, vertically. It just literally goes somewhere else. Imagine it should have been here, but instead it goes boink, and it jumped up there and then continued elsewhere. You might have seen things like this in Algebra 1 when we did piecewise functions, if you remember those things. But that's what a jump discontinuity looks like. An entire chunk of the graph moved vertically away from where basically it should have been. Now, for these next two pictures, they are both examples of a removable discontinuity. Here, there's a hole in the graph. That's what the little open circle represents. And here, there's the exact same graph with a hole in it. Difference between the two is this one is showing you that this single point in space, which should have been right there, was actually way up here. This is not a jump discontinuity because only a single point moved. The difference between the two is here an entire chunk of the graph moved, here a single point moved. A removable discontinuity will be represented by a hole in the graph, a missing point, a deleted point, you might have even called it in Algebra 2. Fancy term, removable discontinuity. It's because literally there's just a hole in the graph. And then the last one, for now, it's called an infinite discontinuity, which our example that we found range up above had an infinite discontinuity in it. An infinite discontinuity will be represented by a vertical asymptote. Should remember those, hopefully, from Algebra 2. This is a vertical line that your graph will get incredibly close to, but never touch. We call it an infinite discontinuity because the graph will shoot up to positive infinity or down to negative infinity at that vertical line. But it will never hit this x value. It'll just shoot towards one of the infinities. So I know I didn't draw it on my picture, but I did have an infinite discontinuity right here at x equals 0. Why? Because you cannot divide by 0. So oftentimes an infinite discontinuity will occur in a place where you tried to divide by 0. That's most often where they happen. So, jump discontinuity, whole piece of the graph moves. Removable discontinuity, a point is either missing or a single point has moved vertically. Infinite discontinuity, graph shoots up or down to one of the infinities at an x value, creating a vertical asymptote. Cool with those? Again, on my test, what you'll have is a picture of a graph, and it'll just say, what kind of discontinuity are you looking at here? And you just, it's multiple choice, and you would just pick one. Okay? There are other types of discontinuities that we will learn about at the end of the year when I'm teaching you AP Calculus. So here we're going to look at A, B, and C. And then I'm going to ask you, looking at these graphs, which of these three figures are discontinuous at x equals 2 according to our authors? I have to say it like that because they're actually wrong. But, well, yeah, I don't like the way they said this. But anyway, these three. Which of these three are discontinuous at x equals 2? What do you got for me? A is one of them for sure. We have an infinite discontinuity here. Infinite discontinuity at x equals 2. And Colin?
C, I believe.
And C. What kind of discontinuity there? Well, just a hole in the graph. Removable. Oh, sorry, Craig, you about to answer?
Yeah.
Might be. Removable. There we go. Yeah, it's a hole in the graph. Just visual vocabulary is what I like to call that. It's what I called it when I was in geometry, like when I was teaching geometry. Like, look at this picture. What do you see? Oh, vertical angles, things like that. So look at this picture. What do you see? Oh, I see an infinite discontinuity. I see removable discontinuity. They didn't need it, but you might as well throw it on there. Vertical asymptote, infinite discontinuity. Let's talk about another feature of curves. This is something that you should have learned in Algebra 2, but I'm not sure. It just depends on who your teacher was. Talking about increasing and decreasing. The way that I describe to increasing and decreasing to my students in Algebra 2 when I teach Algebra 2 is imagine your curve is a roller coaster. We read from left to right in our language, so I would like for you to read your graphs from left to right. So you imagine you plopped a roller coaster car down right here, and as you started going to the right, what was your car doing? Well, this one was going up forever. I know it kind of gets almost flat, but it's not. It will still be going up forever. This is an increasing function. It never stops going up. What is the actual definition of increasing? Positive slopes. That's what that means. Everywhere that you could draw a straight line that touches this curve, the slope of that line would have been positive. So that's what it means to be increasing. So the opposite of that logic would be if your roller coaster is falling as it goes to the right, or negative slopes at every straight line you could draw, that is a decreasing portion of a function, or even a decreasing function. Some functions decrease forever. Some functions increase and decrease, like this one. If you were riding your roller coaster, you'd be decreasing for a while, and then you'd be increasing. Now this one is a slope of 0. If you're riding this roller coaster, you're not going up, you're not going down. This is considered constant, not increasing or decreasing. It's just constant. Its slope is 0. And then this one right here, just like the parabola I showed you up above, have zones where it is increasing and zones where it is decreasing. However, our authors have their heads firmly lodged in their butts because this is wrong. And when I say it's wrong, I mean according to most mathematicians. And this is the kind of thing that mathematicians argue about, but I'm going to show you what's in your AP Calculus textbook, and I've already confirmed with Ms. Bluebaum that she agrees with me. These authors are not correct. If I have my roller coaster car parked right here at this point, is it increasing? Is it decreasing? Is it constant? I mean, what is it? I mean, couldn't we make the argument for it being decreasing and constant at the exact same time? I mean, it's constant here, it's decreasing here, so if it's right there, what is it? Ah, but you're assuming it's moving. What if it's a snapshot? What if it's the picture of the roller coaster as you were riding it, and you just saw it sitting there with nothing in the picture that could show you relative motion, like your hair is not blowing in the breeze, it's just like an image. Was it decreasing, or was it constant? Or was it both? Or was it neither? You see, the bracket that they've used here says that it's decreasing and constant at the same time. How could a number be, let's say slope, how could your slope be 0 and negative at the same time? That doesn't make any sense at all. So, sorry, Watts, Damana, Foley, you are wrong. These should have been parentheses, not brackets. It's impossible to be constant and decreasing at the same time. It's impossible to be constant and increasing at the same time. They're just, and AP Calculus proves my point, so when I get to quarter 4, I'll be able to harp on this a little bit more. When I teach you the AP Calculus, that shows you that I'm right. Okay? So, what I'm going to tell you though is, you know what? That's not yet. That's the next lesson. Never mind what I was about to say. Just for now, it's impossible for you to have a slope of 0 and positive or negative at the same time. Zones of change from increasing to decreasing should always be parentheses, never brackets. Our authors are intelligent but stupid intelligent people. So I'm going to call it right here. We're going to get through this example, and I think that's where we're going to stop. That way I don't have to have these notes chopped up in a weird place. So for this one, it does again say use a graphing calculator. If you don't have a graphing calculator, then by all means use Desmos. I'm going to remember that my camera is not recording the screen, so I will grab a graphing calculator rather than use Desmos. Even though I'd rather use Desmos because it's neat. And I'm trying to avoid that glare that's on my screen. Maybe I do like that. There we go. That's better. Okay. Let's turn this bad boy on. We'll go to y equals. And I'm going to type exactly what I see here. Parentheses, right there, above the 8. X plus 2, x plus 2. Close parentheses above the 9. And then there is an exponent of 2 button right here. I said this yesterday, but there's a good chance that the last time you graphed something, you had a custom window. So rather than wait for it to graph your curve in a weird custom window, I just got in the habit a long time ago of hitting zoom and then typing the number 6. That way it goes ahead and takes me to a standard graph, grid, I should say. So what we've been asked to do is tell where this thing is increasing and where this thing is decreasing. This is a parabola. Can someone describe to me the place, not the numeric value, just the place where every parabola is going to change from increasing to decreasing or vice versa? Looking for the vertex. What now, Damien? It doesn't have to be the bottom. What if it's a parabola that points down? Then it would be the top, right? So what we want to say is the vertex, because regardless of up or down, the vertex is always going to be the zone where the parabola changes from one to the other. At what x value can we find our vertex?
-2.
-2, yeah, that's what makes the inside equal 0. So to the left of -2, is my graph increasing or decreasing? Decreasing. So we will say decreasing. And instead of saying when x is less than -2, we're going to describe all the numbers that are less than -2 using interval notation. From -infinity to -2, parentheses. I don't care if the authors say bracket, they're wrong. So if it's decreasing to the left of x equals -2, guess what it's doing to the right? Increasing. That roller coaster's climbing after that. Does it say constant? Nope, increasing, decreasing. We're constant at the vertex. Last example for the day. Trying to avoid the glare that's on the screen. There we go, I got it. Y equals, clear. Stacked fraction, again, can be found in the math menu, or you could do alpha y equals. That's a shortcut. Alpha y equals brings up the little fraction menu, and I can just hit enter on f over d. Or I could hit math, scroll to the fraction menu, again n over d. Either way, stacked fraction. We have x squared on the top, and on bottom we have x squared minus 1. I'm still on the standard window, so I'm just going to hit graph. What is going on there? Whoa! Holy cow, look at that thing. Ah, you didn't get that? Let's check your equation. Did you type it correctly?
I don't know how to get that little bar. I just pressed divide by.
Well, okay, so those of you that press divide, hey guys, hey, I'm trying to teach you how to use your technology and you can't hear me. If you just press divided by, like some of you did do instead of using alpha y equals, like I said, again, I'll show you one more time, alpha y equals, n over d is numerator over denominator. Could you just use divide by? Yes. However, your calculator is bound by the order of operations. If you type this, whoops, I forgot my divided by symbol. What your calculator is doing is x squared divided by x squared, which is 1, and then it's subtracting 1. what you need to do for that is use parentheses. You have to tell the calculator all of that is the denominator. Okay? So I'm going to scroll the answer real fast because I had to shut everybody up too many times. We are increasing to the left of -1. We are increasing from -1 to 0. And decreasing everywhere else.
He said Walgreens off of Pine Brook where Publix is, but you have to make it a